Welcome to my PILS lecture on how to measure 3D structure while driving or flying. You can see here the data, 3D data that has been recorded with a 3D measurement system from a plant, from a tomato plant, and you can clearly see that this is a three-dimensional information. You can see, look at it from all the sides, and it's just not only a picture or an image, but a 3D structure. So what can you do with 3D structure? I just have again an example from agriculture where we observed these tomato plants or maize plants over time, and then you can generate different things like the involvement of the leaf area, the stem volume. You can estimate potentially the leaf angle distribution, which in this case was from a soybean field, or you can estimate the plant height, as in this example, which has been taken from a wheat field. I will not talk about today about how to generate those parameters and what of them are important and so on. I will just focus on how to generate these data, how to generate 3D point clouds from objects that I'm observing. So first, let's have a look what a 3D structure actually is, or what does it mean in terms of data. So this is a 3D point cloud of this object here, and it's basically only an unstructured collection of points, right, which have x, y, z coordinates, and potentially some additional parameters like RGB values, so they can have a color. Like in the file, this would be would look like this. In this case, it's an east, north, and height coordinates because it's a global coordinate system. And then we have RGB values. So each point has basically 6 numbers, and all these numbers are just listed in the file, and together it then gives this 3D point cloud. And how can we get those point clouds? This is what I want to talk today about. Why am I also talking about flying or driving? So we often generate those point clouds with mobile systems. So we have this example here of a mobile mapping bus where we have a sensor system here. We drive through the city. Here the example of the Geodesy tunnel. And then we measure our surrounding in 3D. We also have a drone which does a similar thing, also has a laser scanner, flies over fields or over large areas which we want to monitor or map. And another example here is our robot that we used last year to generate these nice point clouds from plants in the field. So when you drive or fly through the environment where you measure, you can get much faster, much larger areas, as in this example of the Poppelsdorf Allee, which took us a few minutes to generate this data set. Yeah. What can you do with those more larger scale areas? You can build city models, as in this example. You can do road monitoring to detect cracks and problems in the road, tunnel inspection, clearance profiles, maybe for rail tracks or streets. And you can also have applications in agriculture and forestry, as here where a forest has been mapped to generate information about the trees. Good, how do we do that? And let's start with a very simple example where we take a system which gives us a position, which is this GNSS device here, GNSS antenna with a stick, and we just go, let's assume we have the task to generate a crop surface model, like we want to measure the surface of a field of some plants using a GNSS receiver. No one would do that, right? But it serves just as a simple example where we go there with our stick, we hold it vertical, we know the length of the stick, we measure then we go to the plant and just touch the surface of the plants and measure the points, right? And with this, we can generate a point cloud looking like this. Each of those is a GPS measurement of the tip here of that measurement device. Okay, so the only thing we need really is a sensor system which generates positions. So of course this is no one would really do that, right? You wouldn't go, the accuracy is not very good, the density is not very good, so it would take like weeks to map a field. So we could do it more advanced and more automated by using mobile systems and sensors. So in this case, we don't touch the plant and the surface to measure it. We just use some optical measurement device which can measure the distance and which can generate information about 3D structure of the environment. And then we use this sensor, we attach it to the platform, and then we fly over the field, over the environment, or we attach it to a moving vehicle. And in this case, we can generate point clouds with a higher density and in faster time. So what do we need here? Of course, not only the position of the GNSS antenna here, which we still have, right? We don't need only the position, we need more. We need to know how the platform is oriented, of course, because it's not always vertical. Yeah. We also, of course, need the sensor and the data, which is actually generating our 3D information. So that, just as an example, with the robot that I mentioned already. So here we have this vehicle, we have this sensor here measuring downwards to the plants. Then we drove with this system here, this red track over the field to generate information like this. So this is a 3D point cloud which is generated during the motion of the vehicle. So that summarizes basically what I will explain today. Okay, so we have two parts here. The first part is how to measure 3D. So what exactly are the options to get this information, the distances, and how to measure three-dimensional information, not necessarily while I'm moving or flying, but just in general. Okay, and the other part of it is because we move or fly, we need to know the exact position and orientation of the sensor the whole time it is measuring. And this is the second part of today. I want to explain a little bit how this works. And then you can see how this comes together and how we can measure 3D structure while we fly or move. Okay, how to measure 3D? There are basically two different principles when you measure 3D. So 3D measuring means basically that I somehow determine the distance to an object, right? Because then I can get the three-dimensional information. So how do I do that? There are basically two options. One is, here's my sensor, right? And here's my object. One is I have a sensor which directly is able to measure this distance based on whatever principle. And these sensors are called time-of-flight based methods, right? It's basically a distance sensor, right? And the other option is, if I don't have a distance sensor, then I can use angle sensors, right? If I have 2 points here, one here and the other one here, and I know the distance of those 2 points, and I know the angles to the object from both points, then I can use triangulation-based methods to calculate the distance, right? So this is possible, and these methods are called triangulation-based methods. So measuring the angle from 2 points, knowing the distance of the 2 points, I can get the third point, the distance. And those two principles are the principles which are basically used in all 3D measurement devices. One are the time-of-flight devices and the triangulation devices. And then we have some other segment like categories here, which is LIDAR, time-of-flight cameras, and then some different methods how they work. And then we have here passive triangulation and active triangulation. And I will also explain how these different methods here in this case work. These principles are very often used in many applications, right? I want to mention just a few where we really use them. So our drone with the laser and the robot that I showed you, also autonomous cars which have lasers on the roof and which rotate, they all use lasers, right? So all LIDAR measurements, which is a time-of-flight based measurement. Yeah, and then the drones covering large fields and measuring crop surface models that you may have seen, they use another triangulation based method, which is called multi-view stereo. And then there are other sensors like this one here, which I showed, which was used to generate these high resolution tomato plant from the beginning, and also the plant eye. They use light section methods, which is an active triangulation principle. I want to go now through all these principles and give you a rough idea how they work. So let's start with the LIDAR, with the LIDAR systems. So what we do here in the LIDAR system is just measuring a distance using a laser scanner. You send the laser scanner out to the object, and then it comes back, and the time it uses to go to the object and come back is somehow measured in the device and can be transferred to a distance because we know the speed of light. So this is a LIDAR which uses time of flight measurements. There is a different principle which doesn't send pulses and wait until they come back. They send a continuous wave and then compare the returning wave, compare the phase between the transmitted and returning phase. And this is just a bit more accurate. So you can go down to millimeter or even below millimeter accuracy with this so-called phase shift devices. Now we have one distance, but how do we get from one distance measurement to a full 3D information? So this is done mostly mechanically, right? So here, in this case, we have this laser scan, this laser measurement that you can see here, and there's a mirror and it rotates. And with this, we can generate, and it measures very fast, up to a million points per second, and then you can generate these area views, or if you add another rotation, yeah, to another mirror or another rotation of the whole device, then you can generate a panoramic view of the surrounding with a single distance measurement laser. Okay, just needs to be very fast and rotating, and then we generate this point clouds of the surrounding. There are other scanners which just do profiles, yeah? So they just measure one circle, and then they rotate that, and the third dimension comes through the motion of the scanner, but this is a different story. So then there are time-of-flight cameras. Time-of-flight cameras are not just a single laser distance measurement and then some motion. They try to, they're a little bit like a camera, but they try to measure the distance for each pixel of that camera. And there are different principles how that works. I don't want to explain them. They're basically very similar to the time-of-flight or the phase shift measurements, but they give you a one-shot depth image for each pixel in that time-of-flight cameras. They're usually not that accurate as a laser scanner, but of course the advantage here is that you get the full matrix of ranges basically within one time frame. Okay, so this is a time-of-flight based methods, and now I want to talk about the triangulation based methods. So triangulation, passive triangulation is something where we observe, as I said in the beginning, one point here, the object point that I want to measure the distance that to from two different angles. So here is one camera which sees that object point here in some pixel, and there's another camera which sees it in another pixel, and using these cameras here we can determine this angle. Yeah, we can also determine this angle. And if you know the distance between the two cameras, which is called the baseline or the baseline distance, then you can calculate this distance set. This is a principle behind stereo vision. Stereo vision is what we also do with our eyes, and what we generate. In this case, we generate depth images, which is basically a matrix of ranges for each pixel. Okay. So this is called passive triangulation. It's called passive triangulation because we don't use any extra light source. We just use the light that anyway comes through the camera. So if you add more cameras, you could do the same thing as well, right? So you just extend this to multiple cameras, or you just use one camera and move it around and take pictures consecutively, right? So of course you have to assume that the object is not moving during that time, so it should be static. But with this, I can fly, for example, with a drone over a field and then generate many of those images and do the similar thing, finding points in here, which I see in multiple cameras, and then do a lot of geometry, triangulation to generate, to measure where the actual points in the object has been. And this is called multiview stereo, contains some algorithms which are called structure from motion. Don't want to go into details at all here, but this is something that you may have seen, and it's based on this idea of geometry and seeing points in multiple images. And with this you can generate point clouds as well. Like you can see here, a point cloud of a surface of some, I think it's a wheat field. So then there's something called active triangulation, and it has the same mathematical background, but here we're not looking at the object from two different sides. On one point, we emit some light, and which is then reflected to the camera, right? And if we know the relation between those two, we can again get two angles and measure the distance. Yeah? So in this example, if you have the object here, and we have the light source pointing here, then we see it here in the camera in this pixel, and if the object comes closer, yeah, then this point in the camera may move here, the reflected point. And this, you can transfer this pixel here to an angle, and then you can measure again the distance to the object. This is called active triangulation because we have a light source which is emitting light. You can also have a light source emitting light and then combine it with passive stereo, so meaning that you have two sensors, but that's just an extension, but the same principle behind it. This type of sensor is used here, as I already said, in this very accurate laser scanning system which was used to generate those super high resolution plant point clouds. And there is another thing which you may know, it's a so-called plant eye, which is a sensor which is specifically designed to measure plants, crop surfaces, like you can see here. It also uses a light section sensor or laser triangulation sensor, which is based on active triangulation. And just to have the list complete, sometimes there are some patterns projected to the object. Like here, this is a pattern which was used in the Microsoft Kinect, which was one of the first of those sensors which was commercially available. And they project the pattern to the object and then film this pattern with the camera. And they can also do this triangulation based reconstruction of the 3D structure of the object. Good. So these are the measurement principles that we have for 3D measurements. So what if we now do this in motion? Okay, so here we have now the sensor, and it gives us information of some point in the sensor coordinate system. Right? The sensor coordinate system here, Z coordinate, X and Y. So it's a coordinate system which is attached to the sensor. What we want to have is we want to have this point in some sort of global coordinate system. So we want to have a coordinate which is not some X, Y, Z of the sensor. We want to have it like, for example, an east, a north, and height value in some global coordinate system. And we want to have that while the sensor is moving through the environment attached to some flying vehicle. Okay? So that means what we need to do is we need to generate this transformation, which transforms the coordinate system from the sensor into the coordinate system of the world, like the global coordinate system. This transformation consists of a position, a translation, and a rotation. And we need to determine this translation and rotation in order to be able to transform this local point in the sensor system to some global point coordinate in the global system. And this estimation of this transformation here is called trajectory estimation, because the trajectory contains of positions and rotations of our vehicle for every time that the sensor does a measurement. So how do we determine the position and rotation of the sensor during motion? And this is what I'm going to quickly explain now. So the position, how to get the position of the device, you already know, because this has been nicely explained in the PILS lecture by Heiner Kuhlmann. You can use GNSS for that, right? So GNSS is GNSS antenna which is attached to the vehicle. If we want to have centimeter accurate GNSS, then we need some extra reference station, or we need a reference service. And with this, we can generate centimeter accurate GNSS positions. We can do that even in real time. And then we have this problem, at least in good conditions, solved. We additionally the orientation. So what do I mean by orientation? Usually orientation are given by three angles. which gives you the relation between the vehicle or the object and the world. Right? The world is maybe somehow defined by where is north and where is down, and the angles are basically telling us how are we oriented towards north, which is called heading or yaw, and how are we oriented towards down, which we call roll and pitch. Roll is that orientation of the vehicle, right, around the driving direction, and pitch is perpendicular to the driving direction. So these are the three angles which I need to measure. How do I measure angles? There are different options, and I want to go through them quite quickly. So one very crucial sensor are the so-called inertial sensors. The inertial sensors measure relative information. So for example, a gyroscope is an inertial sensor, and it measures the angular velocity. It tells me how fast I rotate. Right? It does not give me an absolute angle like you are 3 degrees from north. It just gives me angular velocity. And an accelerometer is also an inertial sensor. It measures how much I accelerate. Okay, so it can be determined. It can be transformed to a velocity, and this can be turned to a position. But I need starting values. So it's just a relative information that I have. These inertial sensors are very often in every mobile phone has inertial sensors, and they're used for measuring what your hand does. It determines if your sensor is rotated in portrait or landscape mode and all these things. So all of your mobile phones have inertial sensors, as you may know. Another angle measurement device is a magnetometer. A magnetometer is basically a compass. It tells you where north is. Yeah. So this is very often used as well, although there are some issues with it because it's easily disturbed by stuff. And another option is if I use multiple GNSS antennas, not just one, then I can also get some sort of orientation information out of it. So now we have multiple sensors measuring little different things. How do we combine them? And this is another interesting topic. It's how can we calculate or estimate the best possible trajectory out of the data that we have. Let's have a quick look on that. So here we have a sequence of poses. A pose is a position and an orientation. So this is exactly what we want to know at each point when the sensor does a measurement. And so this is a sequence of poses, which we call trajectory. And this is what we want to know. This is what we want to find out. So now we have some sensor which giving us, for example, an observation of the position. Okay, just the X, Y, Z. This is coming from the GNSS. It's not coming every time that we need it, but it just comes once in a while, 10 times per second, for example. So now we have other information, as I said, the inertial sensors, which gives us relative information. So they give us some information about the relation between this time and this time. Yeah? And this we have between all the different states that we want to estimate. Okay? And then there is maybe another sensor which gives us an angle towards north, maybe a compass, which comes once per second, for example. Okay? And the crucial thing is now to estimate this poses here of the trajectory in the best possible way, knowing all these sensor data and also considering their uncertainties, which is of course important. So there are different algorithms doing that. Some of them doing that online, but just recursively updating one after the other every time when the new measurement is available. These are called Kalman filters. Then there are also filters, the estimation algorithms, which take all of the data that they have and estimate it in one batch, which is only possible if we don't need the data in real time, of course, but these ones do it as well. So the good thing is that we have sensor units which can do this quite okay, let's say. Okay, so we have a sensor unit like this one here, just an example. This is the one that we have on our robot as well. It's the dual antenna GNSS receiver with internal inertial and magnetic sensors. So it combines all these sensors already, and it even has some algorithms running on it, which gives you a position and orientation. There are still issues with it, but this is a good starting point because it gives you basically what you need if the conditions are good, let's say. So, problem solved. So everything's fine now with this theory. Well, there are some challenges, and some of these challenges are actually still things which can be also optimized in research and which we also do in our group. So, for example, you need trajectory estimation within a centimeter accuracy. And this is possible, but if GNSS conditions are not so good, then this is difficult. So there might be other options to enhance this accuracy. The actual measurement system is usually very complex, so you need to know how all the different sensors, lasers and cameras and so on are oriented with respect to each other, and they also need to be, they measure at different times and with different rates. So these are things you have to consider when you build these kind of systems. In the measurement domain, so in the 3D measurement domain, you may have the problem that the actual object or the scene is moving or changing while you drive through it. Right? For example, plants in Klein-Altendorf, because of the wind, are always moving like this, except at night. Yeah? And this has to be considered as well. So this is quite tricky, and also the lighting conditions might be very tricky to deal with when you do 3D measurements. And last but not least, of course, the data processing is something which is tricky, because you need to ask how to interpret the 3D data, how to process them to measure object and parameters and information that I want. What do I actually want? What are the relevant parameters? And how do I get from the points to those parameters? And these are also interesting questions. You can see that here in this example, so this is a 3D measurement of 3 different crops with 2 different sensor systems. So this is a LIDAR-based system from a drone, and this is using MULTIVIEW stereo from images from a drone. And you can see that they look very different, and they actually see different things, right? So if you compare here this section, then you can see the outer darker points are from the MULTIVIEW stereo, and the one here more in the inner part of the crop, they are from the LIDAR. So you see different things, yeah? And you can use that, and it can help you, but it can also confuse you, right? So you need to deal with this. What do I actually see when I measure 3D structure, especially in these complex objects? With this, I want to thank you for listening, and I'm open for questions.